To continue our discussion of eigenvalues and eigenvectors, let's go ahead and formally define what we mean by eigenvalues and eigenvectors. So given a square n by n matrix A, we say that a non-zero vector v is an eigenvector of A if there is a scalar lambda such that AV equals lambda v. The scalar lambda is called the eigenvalue associated to v. And just a note here, this is the Greek letter lambda. It is a very commonly used symbol to denote eigenvalues, and we'll be using that in this class. Geometrically, as I'll remind you, we saw in the last video, and we'll be looking at a bit more in this video, if we view an n by n matrix A as a transformation of Rn, then a non-zero vector v is an eigenvector of A if AV points in the same direction as v or in the exact opposite direction and is scaled by some value lambda, and that scalar lambda is called the eigenvalue corresponding to the eigenvector v. So we look at sort of how v gets transformed by A if we end up with a vector that's pointing in the same or exact opposite direction, possibly getting scaled by some value, then we would call that an eigenvector. And we explored kind of the geometry of that. Let's look at our example from that last video. We had the matrix A was 1, 2, 2, 1. We found that if V1 was 1, 1 and V2 was negative 1, 1, then those were both eigenvectors. I think the eigenvalue corresponding to V1 was 3. So we found in particular AV1 was 3V1, and that the eigenvalue corresponding to V2 was negative 1. So we found AV2 was negative V2. And you can see in the picture here that both of those vectors, after they get transformed by A, are either pointing in the same or exact opposite direction as the original vector. V1 getting scaled up by 3, so it is 3 times longer after we transform it by A, but pointing in the same direction. V2 just sort of flipping directly around, the length of it not actually changing. Okay, and so again, same example, we have AV1 is 3V1, AV2 is negative V2. So multiplying by A, and this is kind of more general now, what's one of the points of finding eigenvalues and eigenvectors? If we consider R2 using the basis V1 and V2, the basis consisting of those two eigenvectors, then we can kind of think about what happens to every vector in R2 after kind of transforming by A. It would stretch the vector in the V1 direction by a factor of 3 and flip the vector in the V2 direction. And this is something we'll look at in just a minute a bit further with another example. So here is that other example. So A, this time a bit more complicated. We've got some decimal values. So negative 0.5, 2.5, 2.5, negative 0.5. And we're given these two vectors. V1 is 1, 1. V2 is 1, negative 1. We are asked to verify that these are eigenvectors. In a future video, we're actually going to learn mathematically how we would discover these vectors ourselves given a matrix. But for now, let's just verify that these are indeed eigenvectors. So what do we need to look at? First, we need, let's say, to look at AV1, and we want to show that that's equal to some lambda V1. So we'll just do our matrix vector multiplication, AV1, okay, 2.5, negative 0.5 times 1, 1. And that's going to give us, I guess, negative 0.5 plus 2.5, so 2, and 2.5 minus 0.5, so also 2. So we got 2, 2. Notice that is 2 times 1, 1, or 2v1. So not only have we discovered here that v1 is indeed an eigenvector, but we have found its corresponding eigenvalue, namely 2. Let's do the same game with v2. So a v2 would be, again, negative 0.5, 2.5, 2.5, negative 0.5, times 1, negative 1. And we get negative 0.5 minus 2.5, so that's going to be negative 3. And we get 2.5 minus negative 0.5, so that's positive 3. And so we get negative 3, 3. This is negative 3 times 1, negative 1, or negative 3 v2. So we find that v2 is indeed an eigenvector with corresponding eigenvalue negative 3. So how would we interpret this? Again, this is what we just discovered, that AV1 is 2v1 and AV2 is negative 3v2. So this tells us that when we sort of view R2 using the basis of these eigenvectors, v1 and v2, then we can think of multiplying by A as stretching vectors in the v1 direction by 2, and flipping and stretching vectors in the v2 direction by a factor of 3. So the negative value doing that sort of flipping or reflecting. Let's actually take a look at this. So we have v1 and v2. Remember, v1 is 1, 1, and v2 is 1, negative 1. And what we've drawn here is sort of this eigenvector coordinate grid. So instead of a standard sort of grid you might see on R2, we have kind of shifted things so that we can think of sort of every point we can land on as kind of multiples and combinations, what we would call in this class linear combinations of v1 and v2. And what I'd like to consider is a vector v3. And let's just make v3 be v1 plus v2. So that would be, I guess, 1 plus 1 is 2, 1 minus 1 is 0. So the vector would be 2, 0. And so if we drew that on here, that would actually come out right to here. So this is our vector v3. And what I want to do is consider the action of sort of what happens when we transform v3 by A. So let's look at A v3. Again, just to go back, A is negative 0.5, 2.5, 2.5, negative 0.5. Okay, so negative 0.5, 2.5, 0.5, negative 0.5. And let's multiply that by v3. So we do this math out, we get negative 1, and we get 2.55, I guess just 5. Okay, so negative 1, 5. That on this is going to be here, so here. So negative 1 would get us to here, and then this is 1, 2, 4, 5, so right up to here. All right, so this is A v3. And what I want to do is kind of look at what AV3 is if we think of it as a linear combination of V1 and V2. And so what you can see here is that AV3, we can get there by going, I guess, 2V1 and then minus 3V2. So V3, we can see in this picture, AV3 is 2V1 minus 3V2. So we started with a vector that was just the sum of V1 and V2. And when we transformed it, we got a vector that was the sum of twice v1 and negative 3v2. And so we've kind of added up those, if we go back to this slide, we've added up kind of these two things that would happen to a vector as we transform it by A. We've added up, two copies of v1. So v1 kind of getting stretched by 2, and the flipping and factoring, so this flipping and stretching in by 3 in the direction of v2. And if we were to kind of algebraically think about this, AV3 is A times v1 plus v2, since v3 was just v1 plus v2, which is going to be AV1 plus AV2, But since since v1 and v2 are these eigenvectors, av1 and av2 become, well, av1 was 2v1 and av2 was negative 3v2. So, instead of just summing up v1 and v2, we are summing up the action on any vector using those as sort of our basis for R2. So, kind of understanding the action on these eigenvectors tells us, if we view R2 in a basis consisting of those eigenvectors, tells us sort of what happens to any other vector. And this can lead us to this idea of a change of basis. We saw this in a previous section, and we're going to be exploring this further in this chapter as well, but just to kind of get the conversation started, if we introduce this matrix P, where the columns are the eigenvectors, so if we look at P, how it's constructed, this first column is v1, this second column is v2. Those are the eigenvectors we just found. This matrix converts eigenvector coordinates into standard coordinates. And we'll see later that A can be written as PDP inverse, where P is this, this kind of change of basis, this matrix P that we're introducing above, which converts eigenvector coordinates into standard coordinates. And D is the matrix shown below. It's the diagonal matrix 2, 0, 0, negative 3, which consists precisely of, a diagonal matrix where the values down the diagonal are the eigenvalues that correspond to the eigenvectors v1 and v2. Okay, so sort of a simple construction once you know the eigenvalues and eigenvectors. And D is diagonal. Why do we care that D is diagonal? It is a much nicer matrix to work with for a lot of reasons, but one of them is shown here. So if we wanted to raise a matrix to a really high power, so let's say we wanted to raise A to the 100th power, well, since A is PDP inverse, well, then A to the 100th would be PDP inverse to the 100th, which is just PDP inverse times PDP inverse times PDP inverse, kind of written out 100 times, right? 100 times. But we can sort of reassociate these parentheses. So we can't change the order of the multiplication, but we can reassociate the parentheses to view this as PD times P inverse P times D times P inverse P times D times dot, 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 all the way down, and then eventually one more P inverse. And what's going to happen is each of these P inverse P's canceled to become the identity matrix. And so we get a bunch of, just to clean this up a little, P, D times the identity, times D times the identity, times D times the identity, so on and so forth, P and then P inverse. But multiplying by the identity doesn't actually change things. So this is just P times D times D times D times D, a whole bunch of these. How many of these? Well, exactly 100 of them. So this actually just becomes P times D to the 100 times P inverse. So that's sort of the punchline. Why does that matter? It looks like we've almost made things harder, right? A to the 100, okay, it's P times D to the 100 times P inverse. We still have something to the 100th power. Well, that thing we're raising to the 100th power here is diagonal. And it turns out that to raise a diagonal matrix to the 100th power just involves raising the elements on the diagonal to the 100th power. So D to the 100th is just 2 to the 100th, 0, 0, negative 3 to the 100th. Compare that to A to the 100th, which would be down here, right? This negative, that's our A to the 100th. That would require us to multiply this matrix here by itself 100 times. And so, just thinking about doing that once makes me reach for my calculator, right? Even just a squared would be this thing times itself, right? I'm just going to write that out for you so you can sort of appreciate this. Times itself as you ponder where your calculator is, right? So imagine doing this. I'm just going to draw sad face, right? Certainly doable, especially if you have technology, but that's just a squared. Now you have to do it, all the way up to the 100th power compared to this p d to the 100th p inverse, d to the 100th, done. And then just multiply it by p. We'd have to find p inverse, which is something we've talked about in a previous section. So that's a little bit of work. But once you have all of that, that's d to the 100th. And once you have p and p inverse, why stop at 100? You can go d to the 1000th versus a to the 1000th. Okay, have fun. So we can sort of very easily, once this is possible, once we've done this process here of creating this diagonal matrix, which a little preview of what's to come, we call that diagonalization. I'm going to formally define that later on, but we can do this raising to these really high powers easily. And looking ahead, so we're going to see some applications of this, namely this third bullet, helping us understand long-term behavior of stochastic matrices and dynamical systems. So these raising to the high powers is certainly useful. Something we've seen in a previous section, but we're going to be exploring it further in this chapter. What we're also going to see in this chapter is actually finding eigenvalues and eigenvectors. So far, we've just kind of, been told, hey, here's a matrix, here's the eigenvalues and eigenvectors, right? But we're going to be exploring how we actually do that algebraically. And then, can every matrix be diagonalized? So we're going to ask that question, can this always be done? If I just give you any n by n matrix, can you find this basis of eigenvectors and produce this diagonal matrix? So another question we're going to be able to answer in a future video, but hopefully we have, again, kind of motivated this concept a bit further, shown you another example, and given you a sense of sort of how these can possibly be used, but we'll see more in a little bit.